Humanity grew up hearing stories of gods wielding the magic of words and gestures that then conjured into reality contraptions that moved by themselves and created tangible effects. We have hence in turn always wanted to experience this power of magic, for what led to the autonomous robots of today has its roots in mankind's fascination of the unknown and magical. The story begins with the discovery of the atom by John Dalton in the 1800s with his atomic theory, and then revolutionized by discoveries of the subatomic particles like the electrons by J.J. Thomson in 1897 and the nucleus by Ernst Rutherford in 1911, revealing that atoms are mostly empty spaces with internal structure, not solid spheres. Then Niels Bohr proposed that the electrons orbit the nucleus in specific energy levels, and a lot of the phenomena associated with reality, like light, color, electricity, are a result of the shift in electron levels in atoms. This fundamental realization then led to a plethora of devices which then tried to bring the power of gods to man. Story of the first machine that could run autonomous calculations start in 1830 when Charles Babbage's analytical engine was designed, which could be classified as the first general-purpose mechanical computer. Although never actually built by Babbage, the blueprint of this device is considered the first fully automatic, general-purpose and programmable computer. It was a mechanical device that could perform many calculations including additions, subtractions, multiplications, and division in theory. The analytical engine introduced key ideas that are still used in modern computers, including programmability and memory storage. This was the spark that set into motion the need for machines that could run through mathematical calculations faster than humanly possible to then, in time, surpass the boundary between man and machine. Although the term computer was coined in 1613, the ENIAC, or Electronic Numerical Integrator and Computer, was the first true general-purpose electronic computer, completed in 1945 at the University of Pennsylvania, that could be programmed to solve various complex problems using thousands of vacuum tubes. This then led to the dawn of the modern era. The ENIAC's ability to be rewired and programmed for different calculations like artillery tables or thermonuclear studies made it revolutionary, truly launching the information age. The ENIAC was massive, occupying about 1,800 square feet, roughly the size of a large room or apartment, and weighed over 27 tons. It was built from 40 panels arranged in a U-shape, stood about 10 feet tall, and contained roughly 18,000 vacuum tubes, making it the first programmable general-purpose electronic digital computer. Then the von Neumann architecture-based EDSAC in 1949 and UNIVAC in 1951 became the first commercial-use computers due to their capability to store programs in memory alongside data. This became the foundation of almost all modern computers. Memory, programs, and data thus became the foundation of computation. Thus began the era of computation, miniaturization, and mass integration of machines that could calculate, memorize, and interface with humanity's exploits. Vacuum tubes were thus replaced by transistors in 1947 with widespread adoption in computers by late 1950s, making computers smaller, faster, and more reliable and cheaper. Thus, mainframe systems from IBM 7000 and IBM 1401 series dominated business centers. In 1954 to 1959 emerged the first high-level programming language, Fortran and COBOL, making programming more accessible. And 1960 saw the integrated circuits, or ICs, that put multiple transistors onto a single chip, enabling even smaller and more powerful machines. Mini computers emerged, example DEC PDP-8 in 1965, which were obviously much smaller and cheaper than mainframes used by labs and smaller organizations at first. In 1971, then the microprocessor revolution led by Intel released the 4001, the first commercial microprocessor or a complete CPU on a single chip. This paved the way for the compact, affordable computing that we see today. 1974 to 1975 saw the dawn of personal computers. The MIT's Altair 8800, featured on the cover of Popular Electronics as a kit, is widely regarded as the spark for the personal computer era. It used Intel's 8080 microprocessor and had no keyboard or monitor initially, but was added by hobbyists. Bill Gates and Paul Allen co-wrote Altair Basic for it, leading to the foundation of Microsoft. The Altair 8800 in 1975 is often considered the first personal computer in the modern sense, an affordable microprocessor-based machine for individuals and hobbyists rather than institutions. This directly inspired the next wave with Steve Wozniak and Steve Jobs creating the Apple I in 1976, a single-board computer sold as a kit, followed by Apple II, Commodore PET, and the TRS-80 in 1977, the first fully assembled, ready-to-use personal computers that reached a broader market. In summary, the journey went from giant, expensive, specialized electronic behemoths in the ENIAC era to smaller transistor-based mainframes and mini-computers to microprocessor-based machines to the birth of personal computing with the Altair in 1975. This set the stage for the PC explosion of the late 1970s and the 1980s. While the capability in compute was racing fast towards light speed as explained by Moore's law, that is the doubling of number of transistors on an integrated circuit or microchip roughly every 2 years, while the cost per transistor decreases in the set time. At the back end, something else was brewing. The use of computers to not just crunch numbers but control machines. In 1952, inspired by John T. Parsons, often called the father of numerical controls, work on the first NC machine, a team at MIT's Servo Mechanism Lab, led by researchers including J.F. Reiches, created the first working prototype of a continuous path numerically controlled milling machine, or the first CNC machine. This was a retrofitted Cincinnati Hydrotel vertical milling machine controlled via punch tape or paper tape with coded instructions rather than manual operation. This was publicly demonstrated in September 1952 and marked the birth of automated, programmable machine tool control. This technology revolutionized precision manufacturing, especially in aerospace, by enabling complex shapes without constant human intervention, thus birthing the integration of computer control into real-world operations for the first time. This is where the seed of autonomy truly began. The history of autonomous driving technology, also called self-driving or driverless cars, spans over a century, evolving from early remote-controlled demos to today's advanced AI-driven systems. The story of autonomous driving, to the shock of most people, actually begins in 1925 when the engineer Francis Houdina demonstrated the American Wonder, a remote-controlled Chrysler driving through New York City streets with no onboard driver controlled from a trailing car. This was more remote operation than true autonomy, but sparked public interest in driverless cars. Then futurists like Norman Bell Geddes at the 1939 New York's World's Fair envisioned automated highways with radio-guided vehicles. In the 1950s, General Motors and others tested electromagnetic guidance systems with wires or magnets embedded in roads for semi-automated control. Then in 1977, Japan's Tsukuba Mechanical Engineering Laboratory developed the first semi-autonomous car using cameras for road following, reaching speeds up to 20 miles an hour. This marked a shift to computer vision-based autonomy. In Europe, the Project Prometheus from 1987 to 1995 developed advanced highway autonomy, culminating in a 1994 hands-free drive on Paris highways, including lane changes and passing. In the US, the Carnegie Mellon University's Navlab series started in 1986 using neural networks to crunch visual data numbers to go from perception to control. In 1995, Navlab 5 completed no hands across America, steering itself autonomously for 98% of a 2,850-mile cross-country trip with the driver handling only throttles and brakes. From the 2000 to 2007's DARPA Grand Challenges sparked modern-era competition, with the 2005's Stanford 132-mile Mojave Desert Race and the 2007's Urban Challenge testing city driving with traffic rules. These inspired private investment, including Google's self-driving car project in 2009 and later with Waymo. 2010s saw the commercial and consumer integration of advanced driver assistance systems or ADAS, example the adaptive cruise control and lane keeping into high-end cars using radar to gauge distances and speed and cameras to look at finer details. This shift towards generalized autonomy in consumer cars then began with Tesla when they developed the first fully integrated self-driving hardware engineered into their cars at production around a 360-degree surround camera system with no aid or use of additional sensors like LiDAR, radar, or ultrasonics. This vision to perception to reasoning to control based on neural network processing remains the most advanced generalized humanistic autonomous vehicle architecture, and hence the system launched in 2015 named Autopilot, later updated to FSD or full self-driving, is still the template in self-driving across the world in consumer cars with no close second till date. Then Waymo began public robotaxi trials in 2017 in Phoenix, the first commercial driverless service. Companies like Cruise and Baidu followed suit. By the mid-2020s, robotaxis operate in select cities with Waymo and Tesla Robotaxi servicing customers in multiple US areas and others like Baidu in China. Fully autonomous unsupervised driving remain now limited to geofence 3D pre-mapped LiDAR-based systems like Waymo and Zoox, which depend on sensor fusion, LiDAR pre-mapping, and AI plus heuristic coded systems, which hence remain limited in how fast it can expand. With Tesla Robotaxi poised for expansion into all major cities by the end of 2026 to early 2027 and self-driving Tesla semi-trucks hitting the highways this year, the field is quickly shifting towards a company that can offer generalized, expandable autonomy to the masses and businesses as opposed to tailor-made systems that would hence lag behind in expansion and capabilities. The advent of autonomy thus shifted from mechanical radio control to AI, sensors, machine learning and mapping to generalized vision-based autonomy that mimics human intelligence. That brings us to the term robot was introduced by the Czech writer Karel Čapek in his 1920s play RUR, or Rossum's Universal Robots, depicting artificial workers that rebel, thus popularizing the word and fears of a robot uprising. Isaac Asimov later introduced the 3 laws of robotics in his 1942 stories, shaping an ethical framework for automatons. From 1940s to 1950s began the modern robotic era. William Gray Walter built the first electronic autonomous robots, Elmer and Elsie's Tortoise, in 1948 that reacted to light and touch. George DeVos patented Unimate in 1954, the first programmable industrial robotic arm. 1960 saw industrial and mobile robots, with the Unimate, which was installed at a General Motors plant in 1961, becoming the first industrial robot on an assembly line for die casting and welding, revolutionizing manufacturing. Then the Stanford Research Institute Shaky from 1966 to 1972 became the first mobile robot using AI for reasoning, vision, and planning in real environments. 1970s to 1990s saw humanoids emerging with robotic arms like the Stanford's arm from 1969 and Puma in 1972, designed to carry out advanced precision tasks. NASA's Mars rover, example the Sojourner in 1997, then brought robotics to space exploration. Honda's Asimo, which has its roots in 1980s, became an iconic humanoid capable of walking, running, and interacting. During this time is when large language models started being developed, although they have their roots start all the way back in 1950s with rule-based systems and early statistical models like Ngram and HMMs for speech and text. From 1990s to early 2000s, statistical machine translation, which is an IBM model, early neural language models named Bengio et al. In 2003, and neural probabilistic language models started emerging. Then in 2017, the Transformer revolution started, which is considered the true starting point of modern LLMs. 2017's Transformer architecture thus enabled scaling, which led to 2020's GPT-3, which proved scaling works. Then in 2022, ChatGPT made it usable by everyone, and 2023 to 2025 saw Grok, Gemini, Anthropic, Cloud AI, and many more, which then turned into a global industry, racing towards AGI-like capabilities waiting to be integrated into humanoids and indistinguishable even now from human speech. Coming back to robotics or humanoids, from 2000s to the present, we have seen an explosion in robotic and humanoid capabilities with AI, autonomy, and robotics integrated AI. Humanoids like Boston Dynamics Atlas, which started development in 2010, perform acrobatics and complex tasks. Robots now assist in surgery, example the Da Vinci system, explore planets with NASA and other space organizations, vacuum homes, deliver packages, and drive autonomous cars. The term collaborative robots or cobots that work safely alongside humans in factories is now a reality, with Figure Robotics taking the lead, deploying a dozen humanoids in a BMW assembly line in 2025. Tesla's Optimus robot Gen 3 is slated to begin mass production in late 2026 with human-like dexterity, hand and body controls. The Chinese have been headfast in making humanoids as well, with Xiaopeng's Iron Robot at 2025 AI Day stunning people with how human it looked walking onto stage. They too have started integrating humanoids in limited capacity to automotive manufacturing, leading to lower downtime and pilot programs that generate valuable data that then can be used to improve the subsequent generations to reach generalized human-like control and intelligence. Today, as of 2026, robotics blend mechanical engineering, AI, and LLMs for applications in manufacturing, healthcare, logistics, defense, and daily life, with ongoing advances towards general-purpose, highly autonomous humanoid robots. The field continues to grow rapidly, promising even greater integration into society and homes starting this year. In a world tailor-made for humans by humans, the vision that once felt magic now feels near grasp. From self-driving cars to AI assistants to humanoid robots, the world's changing at lightning speed and racing towards the age of singularity when man merges with machine and the magical becomes attainable.